Thank you. Happy to be here. Always fun to be at IMS. Of course, it would be better if we were in person, but happy to make the most of it. So I also want to talk about interpretability in a bit of a different context. And so we're not necessarily going to be talking about scenario discovery in this talk, but I want to talk to you a little bit about what we've been doing in the multi-objective trade-off space. So, when we take a look at the sort of classic loop of how multi-objective evolutionary algorithms are connected to simulation models and these different input scenarios, you can see there's work that's being done inside the evolutionary algorithm for the search procedure. But, assuming that the search has gone well, the step at the end of the whole process is to actually make some sense out of the trade-off. So what can we do with this trade-off to facilitate choosing one of the candidate solutions to move on with and further analyze. So this concept of visual analytics with filtering, inspecting, and then providing insight on the work is what we have been working on for a little bit of time. And so what I want to do is I want to talk to you about the trade-off process. For those of you who aren't familiar with it, I'll talk about what one of these plots sort of looks like. And then I want to cover two recent works that we had in environmental modeling and software to provide tools for you to play around with and try to gain more insight out of these trade-offs. And so multi-objective evolutionary algorithms end up giving you, it could be dozens or even hundreds or thousands of different policies from which to choose. And if you take a look at a two-dimensional example, on the left, you have a scatter plot of the points. So you have moderate cost and moderate risk, for example. One of the challenges with scatter plots is that they're limited in the number of dimensions that they can show. And so how do you kind of scale up to multiple dimensions? Well, you see the parallel coordinate plot, which has gained prominence over the last several years, shown on the right. And so this point is equivalent to the line. And it really gets more interesting when you start to add more points. So we have a lower risk point that has higher cost, and then you can see how that translates over on the right-hand side to the parallel coordinates. And even now, you're going to start to see that things are going to get a little messy because I'm just having black points and black lines. And so it's going to be hard to start to tell them apart. And so, when we complete the trade-off, you can see that the parallel coordinate plot allows you to show these crossing lines, which is really nice because it shows you the fact that you can't have your cake and eat it too. In order to reduce risk, it's going to cost more money. And so, so this then allows us to kind of add dimensions onto the parallel coordinate plot when we have multiple dimensions that we're solving for in the optimization. And so I have two objectives, and then all I have to do is basically add another parallel line and then connect the polylines across the way. Okay, and so you can see a third objective, a fourth objective. And then one of the things that we always do is we use a consistent plotting mechanism. So I have the star here at the bottom just to indicate that this is the ideal region. So in other words, points that have their coordinate lower on the screen means that it does better, higher on the screen means it does worse. And you can see that in order for these points to be non-dominated or Pareto optimal, they are representing different levels of trade-off across these different levels of compromise across these different dimensions. Okay, and so you can already start to see, how you tell these two lines apart. And there are also issues associated with the fact that when these lines come together, you may not know which one is which and so forth. So to take a look actually at a presentation that I gave earlier in this conference, you can see what a real, trade-off ends up looking like. One of the things that you'll notice here is that the way that we've plotted this particular plot, which is from our work in the Colorado River that Nathan was also talking about, was the fact that we just have these points in the background as a cloud, so to say, just so that you can sort of see the range of the values. But obviously, it's really hard to tell apart, all this forest of lines. So one of the things that you can do, for example, is if you use color intelligently, that can help because the color is superimposed upon that cloud. So you can actually see, the idea that you can tell the blue, the red, and the green apart, at least, but then the gray is going to be harder to tell apart. Okay, so what are some things that you can do with this, this multivariate data set that describes, the trade-offs in your problem? Well, there's lots of things that you can do, and I want to talk briefly about two different approaches that we've taken. The first is using statistical modeling to build a relationship between the decisions and the objectives within this set. And that was reported in Smith et al. 2019, and I'll spend a few minutes talking about that. And then the second thing I want to talk about is a visualization library that we put together that actually allows you to create these plots in interactive web browser applications that you can then share with people so that they don't have to code it up themselves and they don't have to have expensive software packages in order to play around with the data. Okay, and because we're going to be talking about two papers here, everything is going to be somewhat concise, but hopefully it will be interesting to you. And so the first one, again, is this statistical model that we built. And I first want to acknowledge my co-authors, Rebecca Smith, who is now at the Bureau of Reclamation and did her PhD with us at CU Boulder, and then Balaji Rajagopalan, who we've worked on a number of these different statistical models over the years. And so the idea behind this study was that we used this concept called multivariate regression trees to build this data-driven relationship between the decisions and the objective performance. And the idea behind that is it's used to supplement a more kind of qualitative reasoning around these trade-offs. So in other words, we want to answer the question, what decision variable values tend to cause objective performance that occurs in these different kinds of groups of outcomes. Okay, and so again, here's an example of another kind of real world example that we did with MOEAs. And so we have objectives shown on the top and decisions shown on the bottom. And this is a planning problem that we developed that mimics water management in the Front Range of Colorado. And the basic idea behind this is that it's a portfolio management problem. So a utility has a number of different options that are shown on the bottom that they can use to increase the reliability of their water supply. So they can build gravel pits, they can encourage conservation, they can buy shares of water, and so forth, okay? And so then all of those portfolios are evaluated across these different dimensions. And so they want to minimize the number of years that they have to put the system into restriction. They want to minimize new supply that they have to go after, or this concept of missed opportunity water, and so forth and so on. Now, one of the things that we did, which was pretty cool, was in Rebecca's dissertation work, we actually held workshops at the beginning and the end of the project. At the beginning, we got feedback from the managers on how to formulate this problem in the first place, associated with what kinds of objectives that they wanted to use to characterize their system and so forth. And then at the end of the project, we actually showed them, we sat them down with Tableau workbooks on laptops in front of this trade-off, and we were able to record what their reasoning was on how they played around with the data and sort of what they did. With some guidance from us, but really like we just let them loose on different trade-offs that we generated. And one of the things that we were actually a little bit surprised to learn is this idea that they kept focusing on the decision variable space, which is kind of funny because in in optimization textbooks, it's not like you really talk much about the decisions. It's just like, this is the optimal value of the objective function, Bob's your uncle, right? And so they kept focusing on the decisions, and they wanted to know sort of why is it that there's this relationship, say, between building the gravel pits and what the objectives ended up being, and so forth. And so we thought that building a statistical model might help us with this. And so just to kind of motivate the information, we're familiar with regular regression trees, the famous example of trying to figure out how to predict the waiting time between Old Faithful eruptions. You can have two clusters that indicate that when you're over here, it tends to be this amount, and then when you're over on the other side, it tends to be higher. And so then when we look at the tree, it ends up looking like this, where there's a split in the data in the, the descriptive variables, and then you have the two outcomes. Now, this is great, but with a multi-objective problem, we need to try to figure out a way to sort of expand that to multiple dimensions. And so this multivariate regression tree, which originally originated in ecology, allows you to account for multiple response variables. And then the idea is that you're trying to get similar distributions in each of the response variables, and then you end up seeing these patterns. So each one of the ending leaves of the tree ends up having a particular pattern. For us, this is going to be with objective function values. And so again, we're using this on this Eldorado utility problem that we created that mimics water management in the Front Range of Colorado. And you can see we had 13 decision levers and then 7 different objectives that we were going off of. So when we go back to the objective space here, you can see what it looks like in parallel space. And then what we end up doing is we end up summarizing this in statistical terms. So here are the box plots, and the box plots are colored consistently throughout the results. And so what we're going to do then is we're going to have these different clusters that are going to have different kinds of characteristics of the outcomes, and we're going to see which decisions ended up leading to that. And we did different climate change scenarios that we were optimizing under, and so you'll see the 1 degree C and 4 degree C scenarios that you can learn more about in the paper. This is what one of the MRT results ends up looking like. And so again, what you can see is that we've basically been able to partition the data into having these different distributional patterns of objective function performance. And as an example of how to look at one of these, you can either go from the bottom up or the top down, depending on whether you're more interested in the objective outcomes or the decisions. Here you can see a particular leaf, and then how you got to that was then these various splits in the data. And you can kind of summarize that then in a table and say that if you want good performance in the restriction objectives, which is shown here, and then various levels of trade-off in the other dimensions, it is likely that you should enact these decisions. You can also go the other way, so in other words, if I have a lower conservation factor, how does that affect my results and so forth. One of the other things that we played around with a little bit here was actually how we can use this to infer properties of different decision variables that end up being robust in not a super rigorous sense, but just kind of qualitatively having similar results across 2 different scenarios. And so when we look at that, we can see that if you take these leaves, they're actually similar in 3 of the dimensions of the decisions. And you can then look at what the objective function performance is across one of the scenarios versus the other scenario. And even though you can notice that the hydrographs that are created within those 2 scenarios are quite different, but it turns out that the decisions, some of these decisions end up being pretty similar. And so you can start to kind of use that as a sensitivity analysis to learn more about your decisions within this optimization. This hasn't been extended to the full-blown RDM or MORDM type analysis, but you can see kind of the link that could be made between those 2. Wanted to talk briefly about the second work that we did with the last remaining minutes. This was also published in EMS, and here this was a software development activity where we were able to create these web-enabled applications within these web browsers. And so the idea here then is that it's a full visualization library that you can use, and it allows you to have nice coding templates to create parallel coordinate plots with a lot of these different kinds of features. And I'll show you briefly what motivates that and then what some of the code looks like quickly. And so the issue that I already kind of addressed earlier in the talk is this idea of over plotting within parallel coordinate plots. And so you can see this mess of lines that are hard to tell apart. And so if you look into the visualization literature, there's a lot of different ways of sort of handling this. Brushing is choosing a subset of the lines and only focusing on those and getting rid of the others. Density has to do with using transparency. So here you can actually see that there's more lines that are clustered in certain locations of the distribution versus others. Using color, obviously, and then bundling, which allows you to get rid of the problem in the middle of the plot where, you know, you don't know from where these different lines came from. And so the idea is that before a line goes from one point to the other, it's actually bundled together so you can sort of see what those groups are. And then obviously combining all of those together can really start to give you a sense. This is the same data from A to F, but you can make a lot more sense of it in F versus in A. And so this all sounds well and good, but it turns out that it's not super easy for somebody to just go in and take all of these features and plug them into a software and just hit a button and then go forward with it, which motivated our work in this area. And so it combines HTML and Java and style sheets, and basically, you know, is all handled through GitHub. And we have plenty of examples for people to actually build applications for themselves. And so you don't really need to know a lot about JavaScript in order to do it. The code is actually embedded into an HTML file. This is one of the examples from the paper. And one of the things that's pretty cool is the idea that you can just kind of layer on different commands into the actual Parasol call that allow you to turn on and off these different features. And so, for example, you can see that we have the different buttons that you can turn on and off, and then you basically just, you know, add on different pieces of code when you want to turn the buttons on and off. We also have URL examples for all of these that you can play around with. And other features that you can add are things like weighted sums, which can be helpful sometimes for people to kind of make sense of multiple dimensions. The bundling and the extent to which that you have, you know, more or less extreme bundling, data tables that are linked to the software, and so forth. And so just to conclude, because I know I'm running out of time, if you copy down this bit.ly link here, I have a Google Drive set up that has the papers, code examples, as well as a copy of a previous presentation that I did, and I'll put this presentation in that folder as well, funded by NOAA and EPA grants, thanks to the students who had hard work on this, and happy to answer any questions.
Great. Thank you very much. Any questions? This looks very cool.
I have a question.
Yeah.
So about Parasol, which I think is a really beautiful visual, right? And it makes the data so much more accessible. Have you done any like testing with this? Is this actually, are people now actually using it now that it is available, or you know, one of the big problems with like research code is like a researcher makes code and then puts it on a repository and says like, and it's accessible. And then, you know, it gets like 3 downloads in 5 years or something. You know, have you managed to push this out somehow?
That's a great question. I wish I had this statistic handy, but I think we have gotten a decent number of downloads. I just don't, I don't have that number.
It's fine. Yeah, okay.
One of the things that we did, and we didn't go so far as to, do, I mean, the example that I gave with Rebecca's stuff was this Herculean effort where we went and we rented these laptops. And I guess Rob and you guys probably have done similar things where it's like we rented these laptops and installed Tableau on every single laptop. And then we had all of this stuff, and it was like this huge thing. That was before we developed Parasol. And so when we had another workshop, it was just more of a show and tell where we kind of showed people that we didn't have people like do it hands-on. We'll probably do a hands-on kind of test with this someday, you know, in another project in the future. And I think that the biggest thing for us was just this idea that you can take it and share it with a person without having to have it be in a software architecture. And I mean, Tableau has its strengths, you know what I mean? It's not like well, I said in my other talk this morning, I'm sorry to get these things confused. With the Bureau, we use Tableau, you know, and it works really well, but it kind of depends if you have like a team that has the training in the software, and they know that they're going to have this analytics and they're going to be doing stuff with it over and over and over again. Something like that can help, but we kind of think that this is good for like sharing more with the general, maybe not the general public, but just it's a lot, the kind of learning curve is a lot easier once you've developed the tool to kind of share it with people. So
no, I definitely agree. Yeah. It's all something I've seen in my research where it's like, if you're talking to stakeholders, like exploratory modeling and deep uncertainty is really cool. And you have these big models and all this like massive data, but then like to people not in our tiny little corner of science, it makes so little sense. Right. And I think these visualizations might be a way to like make it a bit more accessible.
Open up. Yeah. Unfortunately, I think we're out of time. So thanks to all our speakers. This was a great session. Should give all the speakers
yes.
applause. Yeah.
We can give virtual applause, but
yes, yeah. Well, if you clap near your microphone, you can sort of make a sound. But okay, great. Well, good. So thanks all, and this will be available as a recording online, right?
yes. So all of the sessions are recorded and they will be available on the Moodle platform.